This video will look at finding the gradient function of an implicit function. It should really be called a relation, as we will see it as a one-to-many relation. An implicit relation is the opposite of an explicit relation or function, which you will be more used to, such as y equals sine x. This function can be written in terms of y equals x squared plus y squared equals to 5 squared is not an explicit function, it is implicit. You may think it can be rearranged to get y equals, but we would then only be taking either the positive or negative square root, which would erase half the graph, which we will see later. To find the gradient function, we will use the chain rule, which has two ways of looking at it. The first definition of the chain rule will help us relate rates of changes, which will be important in implicit differentiation. The second definition is useful in differentiating composite functions, as it tells us the differential of a composite function is the differential of the outside function multiplied by the differential of the inside function. You can see here that the inside function does not change, and we will see an example of this later. Let's go back to the implicit function x squared plus y squared equals to 5 squared. It may seem odd not to write 25, but to write 5 squared instead, but this shows that this implicit relation is related to Pythagoras' theorem, and we can therefore see that the coordinates on this graph will form a circle as shown in a specific example of the coordinate 3, 4, but also in this short video as we move the point around. First of all, from the graph, I can see that when x equals 3, there are two coordinates, 3, 4, and 3 minus 4. This means it is one-to-many. It also means that the gradient function must rely on the x and y coordinates to discern between the point in the first quadrant and the point in the fourth quadrant. To find the gradient of this tangent at the point 3, 4, we could try splitting the implicit relation up into two functions. One with a positive square root, which will relate to the graph above the x-axis, and one with a negative square root, which will relate to the graph below the x-axis. We could also use the fact that the radius from the centre of the circle to the point 3, 4 has gradient of 4 over 3. And the tangent line is normal to the radius by our knowledge of circle theorems. Therefore, the gradient of the tangent must be minus 3 over 4. Although this gives a solution, it does not give us a general approach to find the gradient function of any implicit function. What if we can't rearrange to get y equals and split the function up? What if we are encountering something other than a circle, so we can't use circle theorems? So we must look to generalize our approach. So we want to differentiate to create this general approach, and we can differentiate term by term as we would in a normal function, where the derivative of the sum is the same as the sum of the derivatives. We can differentiate x squared, and we can differentiate 5 squared, as it is a constant, so any change in x and y will have no effect, so it differentiates to 0. However, differentiating y squared with respect to x is the concept that needs to be addressed, and this is implicit differentiation. This is where we use the chain rule to express this differential in terms of differentiating with respect to y, which we can do, and then multiplying by dy by dx. This gives us 2y times by dy by dx. Some teachers would teach to differentiate y normally and then just stick a dy by dx on the end. It is certainly the way I learned, but I am going to keep on referring to the chain rule as there are no tricks here, and I want to cement in you where the derivatives come from. Now I have differentiated each term with respect to x, I can rearrange to get an expression for dy by dx. As predicted, it involves both x and y, and, substituting in the point 3, 4, I get the same gradient of the tangent I got with the previous method that relies on circle theorems. Before we move on, let's observe a property of this implicit function that you may not have seen in explicit functions. That is what is happening when y equals 0. Here, the tangent would be vertical, and thus the differential does not exist. If we see how that relates to the gradient function, it would indeed not be defined when y is 0, as it would result in a fraction with 0 in the denominator. We will explore this further in a later question. So now, let's make the implicit functions more complicated. As you can see, we have a higher power of y and also a product on the left-hand side. When approaching the differential of any expression, you need to ask yourself whether it is a composite, a product, or a quotient, as this will inform as to whether you need to use the chain rule, product rule, or quotient rule. Here, the left-hand side is a product, so I need to use the product rule. The differential of x times y plus the differential of y times x. And on the right-hand side, I have the differential of y cubed plus the differential of 4, which I know is 0. I will again form the chain rules for differentiating y with respect to x. This gives me dy by dx, and I will form the chain rule for differentiating y cubed. This gives me 3y squared dy by dx. So I now can fill in my missing parts. It is worth being more general here by considering y to the power of n and differentiating this. Differentiating this with respect to x gives me n times y to the power of n minus 1 times by dy by dx. This is why teachers say just differentiate normally and then multiply by dy by dx. Back to the question. I can now rearrange to get dy by dx equals minus y over x minus 3y squared. This will have a horizontal tangent, meaning dy by dx is equal to 0, when y equals to 0. However, if I then use this to find the value of the x coordinate when y equals 0, and I do this by using the implicit function, which is where coordinates on the graph come from, I get 0 equals to 4, which is a contradiction. Don't just leave this as your answer though. You need to acknowledge why this shows there are no points with a horizontal tangent. Put an explanation in to explain, as the exam will usually give you 1 mark for this. Now I want to find where the tangent is vertical. A vertical tangent means the gradient is not defined, it is infinite. This would correspond to when the denominator of the gradient function is equal to 0. This gives me the fact that when x is equal to 3y squared, the derivative would be undefined. I can then use the implicit function to find the point when x is equal to 3y squared. This gives me the coordinate of 3 times 4 to the power of 2 over 3 and 4 to the power of a third as the y coordinate. This next question again increases the complexity of the question, as we have a product inside the cosine function. We have already seen that y differentiates to dy by dx, but what about the cosine of xy? I can see that there is an expression inside the cosine function, so we should use a chain rule. Cosine will differentiate to minus sine of xy because the inside function doesn't change. And I now need to multiply the differential of the inside expression. The inside is xy, which we differentiate using the product rule, which we have done in the previous question. I can now rearrange to get an expression for dy by dx. Now the curve intersects xy equals minus pi by 2 when x is equal to minus pi over 2y. When I am finding coordinates, I always deal with the original function or relation. I can now substitute this in to find my y coordinates of plus or minus root pi over 2. Using x is equal to minus pi over 2y, I can get that x is equal to minus or plus root pi over 2. I can now find the two gradients by substituting these points in. When I multiply the simplified gradients together, I can see I will get the desired result of 1. I will now look at some applications of implicit differentiation. Firstly, we can use this concept to solve related rates problems. I've drawn out the diagram representing this question, with y representing the height of the top of the ladder, and x representing the distance the base of the ladder is from the wall. we can see that the variables are related by the same implicit relation we started this video with. What I also know is that x and y are variables which change with time, so it makes sense to differentiate this expression with respect to time if we want to know about the change in x as t changes, or dx by dt. I can again set up the chain rule to differentiate one variable with respect to a different one to get the differential of x squared with respect to t is 2x dx by dt. A similar result can be found for the differential of y squared, leading to this differential equation. I know as time changes, then y will decrease, as the ladder is slipping down, by 1 meter per second. Therefore, dy by dt is negative 1. I can now rearrange to get dx by dt, and when x is equal to 3, y is equal to 4. This gives me that x is increasing by 3/4 meters per second. It makes sense that x is increasing, as when the ladder slips down, the base of the ladder will move forwards. Whenever you do reach a solution, just consider about the validity of it in relation to the question. Another application is to use implicit differentiation to find the derivatives of inverse functions. I'm going to look at y equals ln x and y equals arcsine x. My first step is to rearrange the expression to make x a subject, giving me e to the power of y equals x. I can now differentiate both sides, and I know that the differential of e to the power of y will be, again using the chain rule, e to the power of y dy by dx. I can then rearrange to get an expression for dy by dx, and can note that, from the original rearrangement, e to the power of y is equal to x, so dy by dx is equal to 1 over x. Arcsine x will follow a similar pattern. I will leave it to you to form the chain rule, but my expression will be dy by dx is equal to 1 over cosine y. The manipulation to get a function in terms of x is more complicated, but I can use the Pythagorean identity for this to get that cosine y is equal to the square root of 1 minus sine squared y. As sine y is equal to x from the original rearrangement, I get the derivative of 1 over root 1 minus x squared. Finally, a differential that has come up in Oxbridge interviews is a differential of x to the power of x. Firstly, let's look at the graph. We can see the domain is x is greater than 0, as this is where the function is continuous, and therefore where the gradient exists. To see why this is true, think about why minus a half to the power of minus a half will not be valid. I can follow a similar process as before. First, manipulation, but this time taking the ln of both sides, and then using the law of logarithms that allows me to take a power out to become a coefficient of the logarithm. I can now differentiate the left-hand side implicitly to give 1 over y dy by dx. I can use the product rule on the right-hand side and then multiply by y. From the original function, y is equal to x to the power of x, giving me a final expression for dy by dx. I have kept the gradient function factorized as it helps one to see where the minimum point will be. When 1 plus ln x is equal to 0, a minimum point will occur, which you can see on the graph. This will be when x is equal to e to the power of negative 1. I hope this video has helped you to see how to differentiate implicitly using the chain rule, and how to implicitly differentiate different types of expressions, as well as introduce vertical tangents and how to find them.